Alright, today we're going to learn about something called solution stoichiometry, which is not anything really that much different than what you were doing before with regular stoichiometry, except for the fact that we're going to now be using concentration in the form of molarity to help us convert back and forth between things. It's just another piece or another tool that you can kind of add into it. A couple quick notes that I want to make to you to remind you about is, one, if you need to calculate the actual concentration of something, it's the number of moles divided by the number of liters. So just remember, it's got to be in moles and it has to be in liters. Those units need to be both moles and liters. Another quick note that I want to make. 0.100 molar is not the same thing as 0.100 moles. That's a key thing. That's an easy mistake to make, and I want to make sure that you guys don't confuse that. So to get back to what we were talking about here and review real quickly, if you remember before, we talked about the whole idea of converting between grams and moles, which is pretty simply just use that good old molar mass that we have. So you have your two different conversion factors where you have moles over grams to go from grams over to moles, and then you have grams over moles if you want to go back and forth between from moles over to grams. This is nothing new. This is something you've been doing for quite a while now. Another key piece is if you want to go from particles, say like molecules or ions or whatever, into moles, then you're going to use Avogadro's number, which if you recall is 6.022 times 10 to the 23rd, and that can be anything from atoms to ions to fluffy bunny slippers if you really wanted to. The new thing that we've been dealing with lately has been moles and molarity. Molarity allows you to go between the volume of a solution and into the moles of it, or moles of something, and figure out the volume that you have. Molarity again is your concentration that you're using, and there's two types of conversion factors you can use. You can use moles over 1 liter, or you can have 1 liter over moles, depending on if you're going back and forth between the two. So that should hopefully just be familiar to you. The big thing to remember is that molarity is equal to moles of the substance over 1 liter of it. And that thing right there is going to act as our conversion factor. So conversion factors, remember, can be used to allow you to go back and forth just by flipping over the units on top of each other. So the other key piece to this with stoichiometry is the idea that you need to be able to go between different substances within a chemical reaction. All the stuff that we have up here in this little mole roadmap is basically just if you're staying with that one specific substance. So sodium chloride grams into volume of sodium chloride, or particles of sodium chloride into grams of sodium chloride. If you want to do the actual part where you go from, say, sodium chloride into a product that's formed during a reaction, then you have to remember to use that thing we learned called the mole ratio. And the mole ratio is what ultimately connects the two different things between products and products, reactants and reactants, or reactants to products, or whatever. And you get that from your balanced chemical equation. So to kind of go through with just a simple example of this, we're going to figure out how many moles of water form when 25 milliliters of 0.100 molar nitric acid solution is completely neutralized by NaOH. Key thing you got to key in on here is this word completely neutralized. Basically that means that you don't have to worry about there being any leftover acid or base at the end of this. It just completely reacts 100%. So first thing you're going to do is write out your balanced chemical equation. So we are reacting nitric acid, which is HNO3, and you know that's aqueous by looking at your solubility chart, or remember that all acids are aqueous. And we're going to react that with sodium hydroxide, which is also aqueous by looking on your solubility chart. Since this is a neutralization reaction, you know that one of the products is going to be H2O, and that comes out in the form of a liquid. And the other product then is going to be the new thing formed between sodium and nitrate. So we have sodium nitrate formed. And you can either look up on your solubility chart or remember that all nitrates are aqueous to get that. Now in other reactions you're going to need to balance this. This one happens to come out balanced already, which is kind of nice. As I said before, in previous problems, write down the information underneath the stuff that will keep yourself organized. So they tell us that we have 25.0 milliliters of this nitric acid solution, and it has a concentration of 0.100 molarity, or molar. We're ultimately looking for the number of moles of H2O. The nice thing is we don't have any information about the sodium hydroxide. It does tell us that it completely neutralizes it, so we know we have enough of this sodium hydroxide to end the reaction, so no limiting reactant is needed. So you don't have to worry about doing the calculation for that, because everything's just going to work out nice and perfect. So now we know that we're starting with nitric acid over here, and we ultimately are trying to get to our moles over here of water. We just have to kind of figure out the way to get there. One thing to remember is these little conversions that you can create with concentration, so 0.100 molar is 0.100 moles over 1 liter of solution. We almost never start with our concentrations. So we're going to start with the 25 milliliters of nitric acid. Now, if you recall, we talked about how you have to have your units for volume not in milliliters but in liters. So you got to show your first step, which is just the simple conversion of 1,000 milliliters of HNO3 for every 1 liter of HNO3. By doing that, you get out of milliliters and you get into liters. Now we're ready to be able to use our concentration to find out how many moles of nitric acid there are. And the reason why we need to know the moles is because we're going to want to use this mole ratio to be able to calculate things out. And you have to have it in moles in the first place. So moles of nitric acid, according to this, our little concentration here tells us that we have 0.100 moles of HNO3 for every 1 liter of HNO3. Liters of HNO3 will cancel out. Now we're in moles of HNO3. Now we're going to use our mole ratio from our balanced equation using our coefficients. In this case, it's going to be a 1-to-1 because our coefficients in front of nitric acid are 1, so 1 mole of HNO3 for every 1 mole of water that is produced. The final step then, of course, is just to plug everything into your calculator and get your answer. And in this case, using correct significant figures, you get this fun number of 0.00250 moles of H2O. So this is just a very simple example of solution stoichiometry. The key thing to remember with stoichiometry in general is this piece right here, which is your mole ratio, which comes from your balanced chemical equation. The other pieces is just remembering how to use your molarity as a conversion factor. So now we're going to look at another example where we're going to figure out how many grams of water form. To do this, we're going to go back to our starting number, and I'm totally fine with you guys going ahead and writing out the fact that 25 milliliters is just 0.0250 liters of HNO3. I'm confident in your abilities to be able to do that. So we just want to basically go from liters of HNO3 into grams of HNO3. So first things first, again, I got to get it into moles of HNO3, again using my molarity of 0.100 moles per 1 liter of HNO3. Our liters of HNO3 will cancel out. Now that I have moles of HNO3, I can use my mole ratio to go from moles of HNO3, which in this case is 1 mole of HNO3 for every 1 mole of H2O. That's my mole ratio, which gets me from a reactant to a product. And then finally, since I'm looking for grams, I'm going to use that other piece where I go from grams to moles using the molar mass of H2O, which is 18.02 grams of H2O per every 1 mole of H2O. Cancel out what you can. You're left with grams of H2O, which is what ultimately we were looking for. So now it's just a matter of plugging and chugging it through. And the answer comes out to be 0.0451 grams of H2O. So that's pretty much it in terms of stoichiometry for solutions. We could do a couple more examples here where if you want to find something other than a product, I can actually go through and figure out how many grams of sodium hydroxide were used in the first place simply by using stoichiometry again. Again, you're going to go back to starting with your initial volume that was given to you for nitric acid. Since you can't go from a volume of one thing into a volume of another, we got to convert it back to moles again. So we use our 0.100 moles of HNO3 per 1 liter of HNO3, which again is just our concentration. Now I'm just going to use my mole ratio to go from moles of HNO3 into moles of NaNO3. And looking at our balanced equation, it's still a 1-to-1 ratio. And if I'm looking for grams, I have to go from moles of NaNO3 using its molar mass into its grams. And the molar mass of NaNO3 is 85.00 grams. Moles of NaNO3 cancel, moles of HNO3 cancel, liters of HNO3 cancel, and so do liters of everything cancels out. So we end up with just our grams. In this case, that comes out to be 0.213 grams of sodium nitrate, so NaNO3. So that's how much sodium nitrate would be produced during this neutralization reaction, in addition to the 0.0451 grams of water that we found in the previous example. Now, if we wanted to find out how much sodium hydroxide was originally used, you can still just use the stoichiometry that we had, again, starting with the starting volume of HNO3. We're going to focus in on that volume. So 0.0250 liters of HNO3. If I want to find out how many grams of sodium hydroxide were used, I first need to figure out how many moles of HNO3 there are again. I understand that this looks like we're doing a lot of repetitive stuff, but again, these are just a bunch of different examples. You probably wouldn't solve all of these in the same problem. Now that I have moles of HNO3, you can hopefully at this point have figured out that you're going to use your mole ratio, 1 mole of NaOH for every 1 mole of HNO3 would be required in this reaction. Again, according to our balanced equation, that's where these numbers come from. These ones are coming from our coefficients. Now that I have moles of sodium hydroxide, I'm going to convert that into grams of sodium hydroxide using the 40.00 grams of NaOH, which is its molar mass for every 1 mole of NaOH. Moles of NaOH cancel. Plug and chug your way through to the end, and you end up with 0.100 grams of sodium hydroxide. That means in order to neutralize all 25 milliliters of nitric acid, we needed 0.100 grams of sodium hydroxide to do that. So at this point, hopefully you have a pretty good grasp on how to do solution stoichiometry and realize that it's not that much different than regular stoichiometry. You're still using our mole ratio from the balanced chemical equation. Now we're just adding in molarity in the sense of being able to convert between moles and liters and moles. I would like you real quick go through and see if you can prove that the law of conservation of mass is upheld in this situation. I'm pretty sure you'll find out that it is. We'll go over it in class. If you do still have questions, make sure you write them down so you can bring them with you, ask them in class. We'll go over all of it. Make sure you kind of get this nailed down before we move on too much more. Thanks for paying attention. Hopefully it wasn't too horrible. See you later.